May 12, 1935. Chicago's Electromotive Corporation Assembly Hall. Steam railroad executives would never forget what they witnessed that morning. A sleek, silver-nosed machine gleaming under factory lights, powered by diesel-electric motors that conventional wisdom declared too weak for serious railroading. Through the hiss of compressed air and the murmur of skeptical voices, EMC engineers prepared to demonstrate a locomotive that would run continuously for months without the coal, water, and maintenance stops that defined steam operations. No massive boilers, no firebox crew shoveling coal, no water towers every 100 miles. Yet these unconventional features created a machine capable of sustained operation that no steam locomotive could match. Railroad executives insisted diesel power lacked sufficient horsepower for passenger service. Operating departments demanded proven steam technology that had moved America for a century. The engineering establishment declared diesel-electric propulsion experimental and unproven for mainline service. But inside EMC's Chicago plant, engineers were preparing something no railroad expert predicted. The EA prototype wouldn't just compete with steam locomotives. It would render them obsolete through operational efficiency that transformed the economics of passenger railroading. The winter of 1934 had brought more than economic depression to America's railroad industry. Declining passenger revenues, rising coal costs, and competition from automobiles and aircraft threatened the very survival of long-distance rail travel. Thomas Crawford stood in EMC's engineering office, reviewing performance specifications for a diesel locomotive that would challenge everything railroads believed about motive power. The age of steam domination was ending, though few railroad men would admit it. No amount of improved valve gear or superheated boilers could overcome the fundamental inefficiency of steam locomotives that spent more time servicing than running. Crawford pulled his drafting papers from the file cabinet and studied the calculations he had refined for months. A typical streamlined passenger train required 2,000 horsepower for sustained 90-mile-per-hour operation across prairie grades. Steam locomotives delivering that power consumed 20 tons of coal and 15,000 gallons of water during a 500-mile run. The mathematics were unforgiving. Traditional motive power with its complex mechanical systems and constant servicing requirements simply could not match the operational availability diesel-electric technology promised. But the solution Crawford proposed made railroad executives deeply uncomfortable. The established railroads, particularly those with major investments in steam locomotive facilities, had already declared diesel power inadequate for serious passenger service. They spoke with authority about proven steam performance, established maintenance infrastructure, and the risks of adopting unproven technology during economic crisis. Harold Mitchell, the chief mechanical officer at Burlington Railroad, had been making his case to railroad presidents all winter, carrying performance projections that promised diesel would revolutionize operations. Crawford had heard Mitchell's presentations where traditional steam advocates dismissed diesel-electric locomotives as experimental toys suitable only for switching yards, not mainline passenger service that demanded power, reliability, and speed. But Crawford had spent his engineering career studying thermodynamic efficiency, understanding how energy conversion worked under sustained operation. He grasped something the steam advocates seemed to overlook. Railroads didn't need maximum horsepower for brief periods. They needed consistent power delivery across thousands of miles without the operational interruptions that made steam locomotives unavailable for service 40% of the time. The challenge Crawford faced was not simply technical, but institutional and economic. Operating a diesel-electric locomotive meant abandoning infrastructure railroads had built over decades. Water towers, coaling facilities, ash pits, and roundhouse maintenance systems represented millions in sunk capital that diesel operation would render worthless overnight. Crawford calculated that a streamlined passenger service from Chicago to Denver required not just motive power but the entire supporting infrastructure. Steam locomotives needed water stops every 100 miles, coal every 200 miles, and major service inspections every 500 miles. A single locomotive required a crew of firemen and engineer, plus maintenance teams at each division point to clean fireboxes, remove ash, and inspect running gear. The diesel alternative promised to eliminate most of this complexity. The EA prototype with its twin 900 horsepower diesel engines and electric traction motors could run the entire Chicago-Denver route, 1,004 miles, without stopping for fuel or service. But railroad executives who had spent careers in steam operations weren't convinced by theoretical promises. Mitchell, the Burlington executive who had commissioned the EA prototype, made his priorities clear during their March meeting. Operating costs were crushing passenger revenues. Every hour a locomotive spent out of service cost the railroad money in lost capacity and fixed maintenance expenses. Mitchell had reviewed EMC's proposals and wanted to know why he should risk his railroad's reputation on experimental technology when proven steam power, however inefficient, was already available. Crawford won that argument, but barely. He convinced Mitchell that diesel-electric propulsion offered proven efficiency from marine and industrial applications. The Burlington had agreed to trial the EA prototype on its premier passenger service, the Denver Zephyr, but the contract came with conditions. The locomotive had to demonstrate sustained operation matching steam performance. Any significant mechanical failures would trigger immediate return to conventional steam power. Most critically, the EA had to prove it could maintain demanding passenger schedules across mountain grades and prairie straightaways without the extensive servicing that steam locomotives required. Crawford signed the agreement knowing he was betting EMC's future on unproven technology applied to the most demanding application in the railroading. The EA prototype represented everything innovative about diesel-electric design: twin 900 horsepower Winton diesel engines coupled to General Electric generators that powered traction motors on each axle. The configuration delivered 1,800 horsepower in a streamlined package that weighed 100 tons less than equivalent steam power. But the real advantage came from operational availability. Steam locomotives typically spent 8 to 12 hours servicing for every 24 hours of operation. The EA could theoretically run continuously for weeks, limited only by fuel capacity and routine inspections that could be accomplished in minutes rather than hours. As Crawford watched final assembly of the EA prototype in April 1935, the full weight of his commitment became clear. Harold Mitchell would arrive for acceptance trials within weeks, accompanied by mechanical officers who expected diesel to fail. The entire railroad industry was watching EMC's gamble with skepticism born from a century of steam supremacy. Only Crawford's engineering calculations and the skilled hands of EMC mechanics stood between diesel-electric innovation and the conventional wisdom that declared such technology premature for American railroads. The EA prototype emerged from EMC's Chicago plant on May 26, 1935. Its streamlined silver body stretched 71 feet. The twin diesel engines mounted on a rigid frame that supported electrical equipment designed to deliver continuous power across thousands of miles. Crawford watched the locomotive move under its own power for the first time, electric traction motors humming rather than the explosive exhaust that announced steam locomotives. Mitchell arrived with his inspection team to review the EA before authorizing its first passenger service run. He examined the diesel engines with visible skepticism, comparing their compact design to the massive boilers and complex valve gear that defined steam power. The Burlington executive ran his hand along the smooth nose section, feeling the aerodynamic shape that promised reduced wind resistance at high speeds, but Mitchell's questions revealed his deeper concerns. "Mr. Crawford, my mechanical officers tell me diesel engines can't sustain the power output required for mountain-grade operation. They say electric motors will overheat under continuous loading, and that your fuel capacity won't support the 500-mile divisions we run between Denver and Chicago." Crawford had prepared detailed responses. The twin Winton engines were rated for continuous operation at 900 horsepower each, delivering power through electrical generation rather than mechanical coupling. The General Electric traction motors used forced ventilation cooling systems that could sustain full load indefinitely. Fuel capacity of 1,200 gallons provided range exceeding 1,000 miles at sustained passenger train speeds. The breakthrough came from fundamental thermodynamic efficiency. Diesel engines converted 35% of fuel energy into useful work compared to hatch for steam locomotives. This meant the EA consumed 1/4 the fuel for equivalent power delivery, eliminating the frequent stops that made steam operations so labor-intensive. Michael Brennan, the diesel mechanic who would maintain the EA during its trials, approached Crawford as the acceptance inspection concluded. Brennan had spent 20 years maintaining steam locomotives before EMC recruited him for diesel operations. His experienced hands understood mechanical systems, but diesel-electric technology represented entirely new territory. "Mr. Crawford, I've memorized the maintenance procedures you provided. Check oil levels every 8 hours, inspect electrical connections daily, monitor coolant temperatures continuously. But what happens when something breaks 500 miles from the nearest diesel mechanic?" "Steam locomotives have problems, but every railroad town has men who can fix them." Crawford acknowledged the concern while explaining EMC's approach. The EA carried complete diagnostic equipment and spare parts for field repairs. More importantly, the diesel-electric design had fewer failure points than steam locomotives with their complex valve gear, thousands of boiler tubes, and precision running gear requiring constant adjustment. The moment of truth arrived on June 1st when the EA departed Chicago with the westbound Denver Zephyr. Crawford rode in the locomotive cab, monitoring instruments that displayed diesel engine temperatures, generator output, traction motor amperage, and fuel consumption. Mitchell occupied the first passenger car, ready to document any performance shortfalls that would justify returning to steam power. The EA accelerated smoothly, electric traction motors delivering instant torque without the slipping drivers that plagued steam locomotives starting heavy trains. As the streamlined train reached 90-mile mobshar across Illinois prairie, Crawford watched the instruments confirm what his calculations had predicted. The diesel engines ran at steady 1,800 RPM, generators delivered consistent electrical power, and fuel consumption remained well within the range calculations that promised 1,000-mile operation without refueling. The EA prototype's early performance exceeded Crawford's projections. The locomotive completed its first Chicago-Denver round trip in 36 hours of actual running time, including passenger stops but no mechanical servicing. Brennan's maintenance logs recorded only routine inspections. The diesel engines maintained steady output across mountain grades that would have required helper locomotives with steam power. Mitchell's initial skepticism began shifting toward cautious optimism. But the real test came during the July heat wave that swept across the Colorado plains. On July 18th, with ambient temperatures exceeding 105 degrees, the EA departed Denver. Eastbound with a full passenger load, Crawford wasn't aboard for this run, remaining in Chicago to coordinate the expanding trial program that would demonstrate diesel reliability to other railroads. The crisis developed 200 miles east of Denver as the train climbed the grade approaching Lyman, Colorado. Brennan, monitoring instruments in the locomotive cab, watched the generator temperatures climb into the red zone. The forced ventilation system that cooled the electrical equipment couldn't keep pace with the combined heat from ambient temperatures and sustained high-power operation on the grades. The engineer throttled back to reduce loading, but the damage had occurred. One of the main generator armature windings shorted due to insulation breakdown from excessive heat. The EA lost half its power output, forcing the train to crawl the remaining grade at 30 mph before limping into the next division point with only one functional diesel engine. Mitchell's telegram reached Crawford at midnight. "Generator failure validates our concerns about diesel reliability. Steam locomotive dispatched to pull EA back to Chicago. Recommend immediate suspension of trials pending complete mechanical investigation." But Crawford refused to accept the simple explanation that satisfied Mitchell's skepticism. He organized a detailed failure analysis, bringing General Electric engineers to examine the damaged generator and review the operational data Brennan had recorded. The investigation revealed findings that transformed the crisis into validation of diesel-electric design principles. The generator failure had not resulted from fundamental design weakness, but from a specific cooling system deficiency that could be corrected. The forced ventilation system had been designed for moderate ambient temperatures, not sustained operation in 105-degree heat while climbing grades. More significantly, the EA's twin-engine design had functioned exactly as intended. Despite losing half its power, the locomotive continued operating on one engine, delivering the train to its destination without requiring replacement motive power. A steam locomotive with boiler failure would have been completely disabled, requiring helper locomotives and massive service delays. The diesel-electric configuration provided redundancy that conventional steam power couldn't match. The vindication came through comparative analysis that Crawford presented to Mitchell 2 weeks later. During the EA's trial period, Burlington steam locomotives had experienced 47 mechanical failures requiring helper locomotives or replacement power. The diesel prototype had experienced one repairable failure but maintained service capability through redundant systems. Crawford explained that the generator cooling deficiency could be resolved through upgraded ventilation equipment already available from General Electric. The modification would take 3 weeks, after which the EA could resume its trial program with enhanced reliability under all operating conditions. Mitchell's response reflected the difficult position he faced. The generator failure had given steam advocates ammunition for their arguments about diesel unreliability. The trial suspension had cost Burlington revenue and embarrassed executives who had championed diesel technology. The resumption of EA trials on August 15th marked a turning point in both diesel performance and industry perception. Crawford had used the forced shutdown to implement not just the generator cooling improvements but a comprehensive enhancement program that addressed every operational concern raised during the initial trials. Brennan supervised the installation of upgraded ventilation systems that could maintain electrical equipment temperatures even under sustained high-power operation in extreme heat. The locomotive received improved diagnostic instrumentation that gave crews real-time visibility into all critical systems. Most importantly, Crawford organized a training program that taught railroad mechanics the fundamental differences between maintaining steam locomotives and servicing diesel-electric equipment. The transformation became evident during the EA's first extended endurance run from Chicago to Los Angeles and return. The 4,200-mile round trip, completed in 8 days of actual operation, demonstrated diesel reliability that stunned railroad executives who had dismissed the technology as experimental. The EA ran continuously for 120-hour stretches, stopping only for scheduled passenger station work and brief fuel stops that took 15 minutes instead of the hours required for steam servicing. Brennan's maintenance logs recorded nothing more serious than routine oil checks and filter replacements. The diesel engines maintained steady output across desert grades, mountain passes, and high-speed prairie running without the performance degradation that afflicted steam locomotives operating far from their maintenance facilities. But the definitive vindication came from comparative performance data that Crawford meticulously documented. During the 3-month period from August through October 1935, the EA prototype accumulated 1,000 miles of passenger service, an operational availability rate of 94%. Burlington steam locomotives on equivalent service averaged 58% availability, spending nearly half their time out of service for routine maintenance, coal and water stops, and mechanical repairs. The economic impact transformed railroad executives' perception of diesel technology. Crawford's cost analysis showed the EA consumed fuel worth $1,200 for operations that would have required $4,800 in coal for equivalent steam power. More significantly, the reduced servicing requirements meant the single diesel locomotive could perform work that previously required 3 steam locomotives in rotation to maintain continuous service. Harold Mitchell witnessed the final demonstration that converted him from skeptic to diesel advocate. In November 1935, Crawford arranged for the EA to operate the Denver Zephyr for 30 consecutive days without returning to EMC's Chicago shops. The locomotive ran 31,000 miles across those 30 days, maintained entirely by division point mechanics using the simplified procedures Brennan had developed. Mitchell stood beside the EA on December the 1st as Brennan completed the month's final maintenance check. The Burlington executive examined maintenance logs that recorded oil consumption, fuel usage, and the minimal wear on diesel engine components and electrical equipment. He ran his hand along the locomotive's smooth nose section, then turned to Crawford with an acknowledgement that represented complete reversal from his initial skepticism. "Mr. Crawford, you've demonstrated something our mechanical department said was impossible. This locomotive has done the work of 9 steam locomotives across this trial period, operating with reliability we couldn't achieve with our best maintained steam power. Burlington will order a complete fleet of diesel passenger locomotives based on the EA design." The breakthrough Crawford had achieved extended far beyond successful completion of a prototype trial program. The EA's endurance trials triggered a transformation in American railroading that exceeded even Crawford's projections. By January 1936, 7 major railroads had placed orders for diesel passenger locomotives based on the proven EA design. The streamlined E-Series production models incorporated every improvement discovered during the prototype's 50,000-mile trial program, creating standardized diesel power that would revolutionize passenger operations across the continent. Crawford maintained detailed documentation of the EA's continuing performance as production E units entered service. The prototype logged 180,000 miles during its first year of operation, operating with 96% availability while handling Burlington's premier passenger services. The locomotive's diesel engines showed minimal wear despite sustained high-power operation. The electrical equipment that had experienced cooling problems during July 1935 now operated flawlessly under all conditions. But the true measure of Crawford's innovation emerged from comparative analysis of railroad operating economics. Santa Fe Railway, one of the first major operators to dieselize passenger service, documented savings exceeding $2 million annually from eliminating coal consumption, reducing water stops, and decreasing maintenance labor. Their diesel locomotives operated 12,000 miles between major service inspections compared to 3,000 miles for equivalent steam power. The vindication Crawford sought arrived through reports from railroads that had resisted diesel adoption. Southern Pacific, which had publicly dismissed the EA prototype as experimental and unproven during 1935, began converting its premium passenger services to diesel power in 1937, after watching competitors achieve operational advantages they couldn't match with steam. Michael Brennan, who had maintained the EA throughout its trials, became EMC's chief diesel maintenance instructor, training hundreds of railroad mechanics in the procedures that kept diesel locomotives running with unprecedented reliability. His training emphasized fundamental differences between steam and diesel operations that many traditional railroadmen struggled to accept. Steam locomotives demand constant attention, Brennan explained to classes of skeptical mechanics. You're always monitoring water levels, watching steam pressure, adjusting valve gear, cleaning fireboxes. Diesel locomotives need routine maintenance on schedules, but between inspections they run without the constant intervention steam requires. The hardest lesson for steam men is trusting that the diesel doesn't need fixing just because it's running so smoothly. By 1940, the EA prototype had accumulated over 500,000 miles of passenger service, operating with maintenance costs 70% lower than equivalent steam locomotives while achieving availability rates that allowed single diesel units to replace multiple steam locomotives in rotation. The locomotive that railroad executives had mocked in 1935 had become the standard against which all motive power was measured. Crawford stood in EMC's expanded Chicago facility in December 1940, watching assembly lines produce E-Series diesels at rates that would have seemed impossible 5 years earlier. The plant that had struggled to build one experimental prototype now delivered finished locomotives to railroads weekly, each unit incorporating refinements discovered through the EA's operational experience. The broader impact extended throughout American industry. The EA's success had demonstrated that diesel-electric technology could handle the most demanding applications, validating similar conversions in marine, mining, and industrial operations. The prototype that started as one experimental locomotive had triggered a technological revolution affecting multiple industries. The EA prototype's operational career extended through 1953, logging over 2.1 million miles of passenger service across 18 years without major mechanical overhaul. Crawford, who had moved on to lead EMC's expanding diesel development programs, made periodic visits to inspect the locomotive that had validated his engineering vision and launched the diesel revolution. The definitive assessment came in 1948 when Burlington's mechanical department conducted comprehensive analysis of the EA's long-term performance. The diesel engines that railroad experts had predicted couldn't sustain continuous operation showed wear patterns indicating they could operate another 1,000,000 miles before requiring major rebuilding. The electrical equipment that had experienced cooling problems during the 1935 trials had operated flawlessly for 13 years and 1.5 million miles. Crawford learned of the EA's final operational statistics through correspondence with Harold Mitchell, who had retired from Burlington after presiding over the railroad's complete conversion to diesel power. Mitchell's letter, dated May 1953, reflected on the transformation that began with Crawford's experimental prototype.